measurement. Physics can also be defined as a branch of science dealing with the study of properties of materials. To understand the property of materials, measurement of physical quantities such as length, mass, etc. are involved. The uniqueness of physics lies in the measurement of these physical quantities. There are basically two types of physical quantities. First one is fundamental. Fundamental quantities are the quantities which cannot be expressed in terms of any other physical quantities. For example, time, mass, length, temperature, etc. Second one is derived quantities. Quantities that can be expressed in terms of fundamental quantities are called derived quantities. For example, area, volume, density, etc. are the examples of derived quantities. To measure a quantity, we always compare it with some reference standard. For example, a rope is 10 meters long. We could say it like that: 10 times, it is 10 times as long as an object whose length is defined as 1 meter. Such standard is called a unit of quantity. Therefore, we can define a unit. Unit of a physical quantity is defined as the established standard used for comparison of the given physical quantity. In which the fundamental quantities are measured are called fundamental units, and the units used to measure derived quantities are called derived units. System International, the units, SI system of units. In earlier days, many systems of units were followed to measure physical quantities. The British system of foot, pound, seconds or FPS system, the Gaussian system of centimeter, gram, second or CGS system, the meter, kilogram, second or MKS system. These three systems commonly followed. To bring uniformity, the General Conference on Weight and Measure in years 1960 accepted the SI system of units. This system is essentially a modification over MK system and is therefore rationalized MKSA, meter, kilogram, second, ampere system. This rationalization was essential to obtain the units of all physical quantities in physics. In SI system of units, there are 7 fundamental quantities and 2 supplementary quantities. These are, as shown in the figure, physical quantities. We have 7 types of fundamental quantities. So first one is length. Length's unit is meter and symbolic representation is m. Mass, unit is kilogram and symbolic representation is kg. Time, second. S, electric current. Ampere, capital A. Temperature, unit is Kelvin, capital K. Luminous intensity, candela, CD. Amount of substance, mole, MOL. Mole is symbol. Second is supplementary quantities. We have two kind of supplementary quantities: plane angle and solid angle. Plane angle's unit is radian and symbolic representation is RAD. Solid angle unit is steradian and symbolic representation is SR. So plane angle and solid angle, you could see uniqueness of SI system. The SI system is logically far superior to all other systems. The SI unit have certain special features which make them more convenient in practice. Permanence and reproducibility are the two important characteristics of any unit standard. The SI standard do not vary with time and they are based on properties of atoms. Further, SI system of unit are coherent system of unit in which the units of derived quantities are obtained as multipliers and or submultipliers of certain basic units. Derived quantities and their units are shown. We have lots of derived quantities. Some of them are as area, volume, velocity. We are taking an example of velocity. Okay, so displacement upon time is known as velocity. Displacement is a fundamental quantity. Okay, and time is also fundamental quantity. We use two fundamental quantities to derive a new quantity, which is known as velocity. Similarly, if we talk about pressure, or we could take an example of area. Area is length into width. Okay, so both the length and width both are fundamental quantities because length is measured in meter and width is also measured in meter. So meter into meter will be meter square, and we got a new quantity, that is area. So we can say that area is a derived quantity. Okay, so these are the examples of derived quantities. Standard length. Length is defined as the distance between 2 points. SI unit of length is meter. 1 standard meter is equals to 1650763.73 wavelength of the orange red light emitted by individual atoms of krypton 86 in a krypton discharge lamp. Mass is the quantity of matter contained in a body. It is independent of temperature and pressure. It does not vary from place to place and its unit is kilogram. The kilogram is equal to the mass of international prototype of the kilogram, a platinum iridium alloy cylinder kept at the International Bureau of Weight and Measures at Servers near Paris, France. An atomic standard of mass has not yet been adopted because it is not yet possible to measure masses on an atomic scale with such precision as on a microscopic scale. Time. Until 1960, the standard of time was based on the mean solar day. The time minus the time taken for 9192-631-770 periods of the radiation corresponding to unperturbed transition between hyperfine levels of the ground state of cesium-133 atom. In atomic clocks, an error of 1 second occurs only in 5000 years. Ampere. The ampere is the constant current which flowing through two straight parallel infinitely long conductors of negligible cross section and placed in vacuum 1 meter apart would produce between the conductors a force of 2 into 10 raised to power minus 7 newtons per unit length of conductors. Kelvin. The Kelvin is the fraction of 1 upon 273.16 of the thermodynamic temperature of the triple point of water. Candela. The candela is the luminous intensity in a given direction due to a source which emits monochromatic radiation of frequency 540 into 10 raised to power 12 Hz and of which the radiant intensity in that direction is 1 upon 683 watt per steradian. Mole. The mole is the amount of substance which contains as many elementary entities as There are atoms in 0.012 kg of carbon 12.